Chapter 1. Building Abstractions with Procedures. The acts of the mind wherein it exerts its power over simple ideas are chiefly these three. 1. Combining several simple ideas into one compound one, and thus all complex ideas are made. 2. The second is bringing two ideas, whether simple or complex, together and setting them by one another so as to take a view of them at once, without uniting them into one, by which it gets all its ideas of relations. 3. The third is separating them from all its ideas of relations. The third is separating them from all other ideas that accompany them in their real existence. This is called abstraction, and thus all its general ideas are made. John Locke, An Essay Concerning Human Understanding. We are about to study the idea of a computational process. Computational processes are abstract beings that inhabit computers. As they evolve, processes manipulate other abstract things called data. The evolution of a process is directed by a pattern of rules called a program. People create programs to direct processes. In effect, we conjure the spirits of the computer with our spells. A computational process is indeed much like a sorcerer's idea of a spirit. It cannot be seen or touched. It is not composed of matter at all. However, it is very real. It can perform intellectual work. It can answer questions. It can affect the world by disbursing money at a bank or by controlling a robot arm in a factory. The programs we use to conjure processes are like a sorcerer's spells. They are carefully composed from symbolic expressions in arcane and esoteric programming languages that prescribe the tasks we want our processes to perform. A computational process in a correctly working computer executes programs precisely and accurately. Thus, like the sorcerer's apprentice, novice programmers must learn to understand and to anticipate the consequences of their conjuring. Even small errors, usually called bugs or glitches, in programs can have complex and unanticipated consequences. Fortunately, learning to program is considerably less dangerous than learning sorcery, because the spirits we deal with are conveniently contained in a secure way. Real-world programming, however, requires care, expertise, and wisdom. A small bug in a computer-aided design program, for example, can lead to the catastrophic collapse of an airplane or a dam, or the self-destruction of an industrial robot. Masters of software engineering have the ability to organize programs so that they can be reasonably sure that the resulting processes will perform the tasks intended. They can visualize the behavior of their systems in advance. They know how to structure programs so that unanticipated problems do not lead to catastrophic, that's a hard word, consequences. And when problems do arise, they can debug their programs. Well-designed computational systems like well-designed automobiles or nuclear reactors are designed in a modular manner so that the parts can be constructed, replaced, and debugged separately. Programming in Lisp. We need an appropriate language for describing processes, and we will use for this purpose the programming language Lisp. Just as our everyday thoughts are usually expressed in our natural language, such as English, French, or Japanese, and descriptions of quantitative phenomena are expressed with mathematical notations, our procedural thought will be expressed in Lisp. Lisp was invented in the late 1950s as a formalism for reasoning about the use of certain kinds of logical expressions called recursion equations as a model for computation. The language was conceived by John McCarthy and is based on his paper Recursive Functions of Symbolic Expressions and Their Computation by Machine, McCarthy, 1960. Despite its inception as a mathematical formalism, Lisp is a practical programming language. A Lisp interpreter is a machine that carries out processes described in the Lisp language. The first Lisp interpreter was implemented by McCarthy with the help of colleagues and students in the Artificial Intelligence Group of the MIT Research Laboratory of Electronics and in the MIT Computation Center. Lisp, whose name is an acronym for Lisp Processing, was designed to provide symbol manipulating capabilities for attacking programming problems such as the symbolic differentiation and integration of algebraic expressions. It included for this purpose new data objects known as atoms and lists, which most strikingly set it apart from all other languages of the period. Lisp was not the product of a concerned design effort. Instead, it evolved informally in an experimental manner in response to users' needs and to pragmatic implementation considerations. Lisp's informal evolution has continued through the years, and the community of Lisp users has traditionally resisted attempts to promulgate, I don't know what that word means, any official definition of the language. This evolution, together with the flexibility and elegance of the initial conception, has enabled Lisp, which is the second oldest language in widespread use today, only Fortran is older, to continually adapt to encompass the most modern ideas about program design. Thus, Lisp is by now a family of dialects which, while sharing most of the original features, may differ from one another in significant ways. The dialect of Lisp used in this book is called Scheme. Because of its experimental character and its emphasis on symbol manipulation, Lisp was at first very inefficient for numerical computations, at least in comparison with Fortran. Over the years, however, Lisp compilers have been developed that translate programs into machine code and can perform numerical computations reasonably efficiently. And for special applications, Lisp has been used with great effectiveness. Although Lisp has not yet overcome its old reputation as hopelessly inefficient, Lisp is now used in many applications where efficiency is not the central concern. For example, Lisp has become a language of choice for operating system shell languages and for extension languages for editors and computer-aided design systems. If Lisp is not a mainstream language, why are we using it as the framework for our discussion of programming? Because the language possesses unique features that make it an excellent medium for studying important programming constructs and data structures, and for relating them to the linguistic features that support them. The most significant of these features is the fact that Lisp descriptions of processes called procedures can themselves be represented and manipulated as Lisp data. The importance of this is that there are powerful program design techniques that rely on the ability to blur the traditional distinction between passive data and active processes. As we shall discover, Lisp's flexibility in handling procedures as data makes it one of the most convenient languages in existence for exploring these techniques. The ability to represent procedures as data also makes Lisp an excellent language for writing programs that must manipulate other programs as data, such as the interpreters and compilers that support computer languages. Above and beyond these considerations, programming in Lisp is great fun. 1.1. The elements of programming. A powerful programming language is more than just a means for instructing a computer to perform tasks. The language also serves as a framework within which we organize our ideas about processes. Thus, when we describe a language, we should pay particular attention to the means that the language provides for combining simple ideas to form more complex ideas. Every powerful language has three mechanisms for accomplishing this: primitive expressions, which represent the simplest entities the language is concerned with; means of combination, by which compound elements are built from simpler ones; and means of abstraction, by which compound elements can be named and manipulated as units. In programming, we deal with two kinds of elements: procedures and data. Later, we will discover that they are really not so distinct. Informally, data is the stuff that we want to manipulate, and procedures are descriptions of the rules for manipulating the data. Thus, any powerful programming language should be able to describe primitive data and primitive procedures, and should have methods for combining and abstracting procedures and data. In this chapter, we will deal only with simple numerical data so that we can focus on the rules for building procedures. In later chapters, we will see that these same rules allow us to build procedures to manipulate compound data as well. 1.1.1 Expressions. One easy way to get started at programming is to examine some typical interactions with an interpreter for the scheme dialect of Lisp. Imagine that you are sitting at a computer terminal. You type an expression, and the interpreter responds by displaying the result of its evaluating that expression. One kind of primitive expression you might type is a number. More precisely, the expression that you type consists of the numerals that represent the number in base 10. If you present Lisp with a number, the interpreter will respond by printing with the number 486. The interpreter will respond by printing 486. Let's try that. Yeah, that works. The interpreter will respond by printing... Oh yeah, I just read that. Expressions representing numbers may be combined with an expression representing a primitive procedure, such as plus or times, to form a compound expression that represents the application of the procedure to those numbers. For example, plus 137. Yeah, that works. I'm not gonna type all of them. Expressions such as these, formed by limiting a list of expressions within parentheses in order to denote procedure application, are called combinations. The leftmost element in the list is called the operator, and the other elements are called operands. The value of a combination is obtained by applying the procedure specified by the operator to the arguments that are the values of the operands. The convention of placing the operator to the left of the operands is known as prefix notation, and it may be somewhat confusing at first because it departs significantly from the customary mathematical convention. Prefix notation has several advantages, however. One of them is that it can accommodate procedures that may take an arbitrary number of arguments, as in the following example. Plus, and then you give it a list of numbers. Yeah. No ambiguity can arise because the operator is always the leftmost element and the entire combination is delimited by parentheses. A second advantage of prefix notation is that it extends in a straightforward way to allow combinations to be nested. That is, to have combinations whose elements are themselves combinations. There is no limit in principle to the depth of such nesting and the overall complexity of the expressions that the Lisp interpreter can evaluate. It is we humans who get confused by still relatively simple expressions, such as the following, which the interpreter would readily evaluate to be 57. Oh. Let's see here. Yeah, that works. Why it didn't color it weird, but blah blah blah. Following a formatting convention known as pre-printing, in which each long combination is written so that the operands are aligned vertically. The resulting indentation display clearly the structure of the expression. Even with complex expression, the interpreter always operates in the same basic cycle. It reads an expression from the terminal, evaluates the expression, and prints the result. This mode of operation is often expressed by saying that the interpreter runs in a read-eval-print loop. Observe, in particular, that it is not necessary to explicitly instruct the interpreter to print the value of the expression. 1.1.2 Naming and the environment. A critical aspect of a programming language is the means it provides for using names to refer to computational objects. We say that the name identifies a variable whose value is the object. In the scheme dialect of Lisp, we name things with define. Typing define size 2 causes the interpreter to associate the value 2 with the name size. Once the name size has been associated with the number 2, we can refer to the value 2 by name. Size 2. Okay, let's try that. I don't know why it pasted the timer there. Define size 2. And now here we can ask it to print size. Yeah, that works. And we can do times 5 size. Here are further examples of the use of define. Define pi, define radius. Yeah, okay. Define is our language's simplest means of abstraction, for it allows us to use wait, I'm reading back. No, they haven't defined functions yet, right? Define is our language's simplest means of abstraction, for it allows us to use simple names to refer to the results of compound operations, such as the circumference computed above. In general, computational objects may have very complex structures, and it would be extremely inconvenient to have to remember and repeat their details each time we want to use them. Indeed, complex programs are constructed by building step-by-step computational objects of increasing complexity. The interpreter makes this step-by-step program construction particularly convenient because name-object associations can be created incrementally in successive interactions. This feature encourages the incremental development and testing of programs and is largely responsible for the fact that Lisp programs usually consist of a large number of relatively simple procedures. It should be clear that the possibility of associating values with symbols and later retrieving them means that the interpreter must maintain some sort of memory that keeps track of the name-object pairs. This memory is called the environment, more precisely the global environment, since we will see later that a computation may involve a number of different environments. 1.1.3 Evaluating combinations. One of our goals in this chapter is to isolate issues about thinking procedurally. As a case in point, let us consider that in evaluating combinations, the interpreter is itself following a procedure. To evaluate a combination, do the following. 1. Evaluate the sub-expression of the combination. 2. Apply the procedure, that is the value of the leftmost sub-expression, the operator, to the arguments that are the values of the other sub-expression, the operands. Even this simple rule illustrates, To evaluate a combination, do the following. Evaluate the sub-expression of the combination. Apply the procedure that is the value of the leftmost sub-expression, the operator, to the arguments that are the values. Okay, so are they saying so you have the environment, which is kind of like a dictionary. And then it says, first look up all of the, this is recursively. Okay, so recursively evaluate the sub-expressions and then try and apply everything to the leftmost thing. Right. I think is what that means. Even this simple rule illustrates some important points about processes in general. First, observe that the first step dictates that in order to accomplish the evaluation process for a combination, we must first perform the evaluation process on each element in the combination. Thus, the evaluation rule is recursive in nature. That is, it includes as one of its steps the need to invoke the rule itself. Yeah, okay. Notice how succinctly the idea of recursion can be used to express what, in the case of a deeply nested combination, would otherwise be viewed as a rather complicated process. For example, evaluating this expression requires that the evaluation rule be applied to 4 different combinations. We can obtain a picture of this process by representing the combination in the form of a tree. Oh, wow, that's really nice. Made like a little ASCII thing there. We can obtain a picture of this process by representing the combination in the form of a tree. Each combination is represented by a node with branches corresponding to the operator and the operands of the combination stemming from it. The terminal nodes, that is, nodes with no braces stemming from them, represent either operators or numbers. Viewing evaluation in terms of the tree, we can imagine that the values of the operands percolate upward, starting from the terminal nodes and then combining at higher and higher levels. In general, we shall see that recursion is a very powerful technique for dealing with hierarchical tree-like objects. In fact, the percolate values upward form of the evaluation rule is an example of a general kind of process known as tree accumulation. Okay. Next, observe that the repeated application of the first step brings us to the point where we need to evaluate not combinations, but primitive expressions such as numerals, built-in operators, or other names. We take care of the primitive cases by stipulating that the value of numerals are the numbers that they name, the values of built-in operators are the machine instruction sequences that carry out the corresponding operations, and the values of other names are the objects associated with those names in the environment. We may regard the second rule as a special case of the third one by stipulating that the symbols such as plus and times are also included in the global environment and are associated with the sequences of machine instructions that are their values. The key point to notice is the role of the environment in determining the meaning of the symbols in expressions. In an interactive language such as Lisp, it is meaningless to speak of the value of an expression such as plus x1 without specifying any information about the environment that would provide a meaning for the symbol x, or even for the symbol plus. As we shall see in Chapter 3, the general notion of the environment as providing a context in which evaluation takes place will play an important role in our understanding of program execution. Notice that the evaluation rule given above does not handle definitions. For instance, evaluating define x3 does not apply define to the two arguments, one of which is the value of the symbol x and the other of which is 3, since the purpose of the define is precisely to associate x with a value. That is, define x3 is not a combination. Such exceptions to the general evaluation rule are called forms, special forms. Define is the only example of a special form that we have seen so far, but we will meet others shortly. Each special form has its own evaluation rule. The various kinds of expressions, each with its associated evaluation rule, constitute the syntax of the programming language. In comparison with most other programming languages, Lisp has a very simple syntax. That is, the evaluation rule for expressions can be described by a simple general rule together with specialized rules for a small number of special forms. Okay, I think I'm going to stop it here because we're almost at 25 minutes.